And with that, it's time for us to move on to our final act for the evening, and time for me to introduce you to our final speaker for this evening. He was born in Chennai and raised in Gujarat. He went to school and college in Gujarat, and thereafter has spent the bulk of his adult life living between the UK and the United States of America. As a child, I believe, he was fascinated by mathematics and wanted to pursue it, but he ended up studying physics instead and obtained a PhD in the subject. But thereafter, he switched to biology, and I imagine that was a life-changing decision for him. Another such turning point might have been when he decided to take on the seemingly impossible task of decoding the structure of the ribosome. Now, if you're wondering what a ribosome is, why this was such a hard task, and why, despite being such a hard task, it was incredibly worthy, I'm going to let our next speaker tell you all of that. But very briefly, just to begin with, approximately you can think of a ribosome as a small molecular machine that exists in our cells and manufactures proteins by deciphering our genetic codes. Maybe that doesn't sound like a big deal until I tell you what these proteins actually do. They practically do everything from carrying oxygen in our blood to helping our eyes perceive light, to forming antibodies that fight disease-causing microbes. In short, living beings would not well be living without these proteins. So hopefully you get a sense of why this might have been a very, very important project. And of course, our speaker managed to succeed in this seemingly impossible task and went on to win a Nobel Prize in chemistry for it. And that's just one of his laurels. He's also won the Padma Vibhushan, he has been knighted, but he's not one to rest on his laurels. He has continued his research just as vigorously, is the president of the Royal Society, and has recently written a book on the research that won him the Nobel called The Gene Machine, which I personally found just incredibly compelling and thrilling. And I know that when you hear or think of a book called Gene Machine, thrilling is not the word that might come to your mind, but seriously, read it and trust me, you'll see what I'm saying. But the thing is, I find his ideas and his thoughts valuable beyond his immediate field of study as well, and think of him as the sort of public intellectual that this country, and for that matter, any country in the world, badly needs at this time. Please welcome Venki Ramakrishnan. Hello, and thank you for joining us. Thank you for patiently waiting for your turn.
It's a very interesting evening, actually.
Thank you for saying that. I'm delighted to hear that. So you studied physics, you obtained a PhD in physics, and then you went back to grad school to study biology, and you won a Nobel Prize in chemistry. You might forgive some members of the audience for being confused about what it is exactly that you do. Would it be correct to say that you would describe yourself as predominantly a molecular biologist who works at the cusp of biology and chemistry?
I think that's a very good description. I think the confusion people have is completely the result of university department organizations. But science doesn't really recognize departments. People pursue problems, and sometimes the problems involve one or more disciplines, sometimes they involve a problem from one area but techniques from a different area. That's very common. So I think these disciplines existed because university grew up and they formed departments. But if you looked at Robert Hooke, a famous early fellow of the Royal Society, you couldn't say whether he was a physicist or a biologist. He discovered Hooke's law and did lots of physics, but he also was the person who coined the word cell to denote the cellular organization of life. So I think this is an artifact that is gradually going to disappear.
Well, I hope so. You've certainly argued for maximum interaction between disciplines in science, and particularly when it comes to higher education. Could you talk a little bit about that? Perhaps also, the sort of edge that your own fairly extensive knowledge of all three disciplines might have given you in your work.
I think my view is that you don't have to, you shouldn't really force people in the direction of interdisciplinarity. There are plenty of great scientists who worked in a single area and made amazing contributions. But what I think we shouldn't have is artificial barriers that prevent people from crossing disciplines as needed. And so that's my view. I think it shouldn't be forced, but it should not be inhibited in any way. So that science follows whatever form it needs. But in terms of my own life, I think my background in physics allowed me to have a feel for signal to noise in these very physical techniques I was using, like X-ray crystallography, to solve the structure of this very fundamental biological molecule. So in that sense, my physics background helped indirectly. But there are plenty of people who use crystallography without really understanding physics, in much the same way that people drive cars without really understanding the engineering or the mechanics of an internal combustion engine. But they use a car to sort of get where they want to go. And a lot of people use crystallography in that way. I think the fact that this particular problem was at the very limit, actually beyond the limit of what had been done, meant that understanding it in some greater depth probably helped.
Coming to the problem that you took on, I would like you to tell the audience as simply as possible what a ribosome is. I did a terrible job of it earlier, but that was just to sort of give them a sense of what I was talking about. But what a ribosome is, why scientists were looking into its structure when you started work on it, and why it seemed like such a difficult task.
So, when the structure of DNA was discovered, people had the rough idea that the 4 bases on DNA were like letters in an alphabet. And so you can think of the order of bases in DNA as a sentence, consisting of different letters. And that sentence coded for something. What it coded for was a protein. Now you heard about how proteins do all sorts of things. Actually, we have 25,000 genes in us, and each one of those genes specifies a protein which actually has its own specific function. So nearly all of the reason we exist, including the form that we have, for example, our muscle and skin, it's all made of proteins. But proteins are chains of a completely different type, and there are 20 types of building blocks for proteins called amino acids. So it's like going from a 4-letter alphabet, which is the alphabet of DNA or a copy of it called RNA, to a 20-letter alphabet. And so biologists call this process translation, because you're going from the language of genes to the language of proteins. And in the 50s, it was a big puzzle. How does DNA even encode this information? Well, now we know a lot about it, but without belaboring the fact, it doesn't happen by itself. What happens is, there's this very large molecule. I know you described it as small, and it's because small and large are context dependent. It's small in everyday terms, in that if you took a width of a hair, you could have 20,000 ribosomes across the width of a hair. So in that sense, it's tiny. But in molecular terms, it's huge. It has 500,000 atoms, okay? So in molecular terms, it's an enormous machine, complex machine. So the whole point was the ribosome was discovered as the object that allows this translation to happen. But nobody had any idea what it looked like. So imagine if you knew nothing about what a car looked like. You know, you were a Martian hovering above the Earth, and you'd see these little objects moving around and moving along in straight lines and turning at right angles. That is if you're in Houston. In Bangalore, it's a different story. But anyway, you wouldn't have any idea what a car was or how it worked. Then you get closer and you start seeing roughly what a car is put together. But it's only when you look at a car in detail that you know it's got an engine, it's got pistons, it's got things that fire, fuel injection, it's got a crankshaft that connects the engine to the wheels. So then you start understanding how a car works. And it's the same with a molecule. And the more complex the molecule, the more you need to really know what it looks like. So after the ribosome was discovered, the big quest, which lasted about 30 years, was what does the ribosome look like, and how does it carry out this amazing process of synthesizing proteins by reading along the genetic message?
I want to talk to you a little bit about how and when the breakthrough came through, but before that, I have wondered while reading your story. By the way, the Gene Machine is, of course, it is about the research that got Venki the Nobel, and he's best known for, but it's also a sort of, speaking of DNA, a sort of double helix, because it's also a kind of memoir. And therefore, it's a simply fantastic read. And while reading it, I couldn't help but wonder that here you were, you'd already made a career shift, which seemed to be a pretty radical choice. And thereafter you go on to take on this seemingly super difficult problem that you may never be able to really solve, instead of opting for a safer route when it came to research. Do you remember what made you make that decision? Was it a hard decision to make?
Well, I was working on ribosomes, and I was also working on something else. My lab was divided in sort of two parts. But it occurred to me that the big question in the field was tackling, the structure of the entire ribosome. That was the thing that would allow us to get to the next step. And there had been this group headed by Ada Yonat, who had actually pioneered getting the first crystals of the ribosome and really paving the way to show that it might be possible. But this group had been around for 15 years and no progress was being made. And I realized that, if I didn't do it, and then I knew that a group at Yale was thinking about it, including my former mentor. And I realized, sorry about my cough, but I realized that if I didn't do this, I would watch it be done by other people and then sort of regret it for the rest of my life. But if I gave it a shot and failed, then I probably wouldn't regret it. I would say, okay, I gave it a good shot, and then move on to do something else.
But you didn't fail, and thank God for that. But could you tell us a little bit about how and when the breakthrough came about, how it came about? And I believe there's a story about you at some point dancing in the lab. Do you remember what you were feeling then?
So the idea came to me when I was on sabbatical, and I was using a sort of twist to the standard way of doing crystallography, which uses these very large accelerators, particle accelerators that generate very powerful X-rays called synchrotrons. And the thing about these synchrotrons is, unlike the X-ray in your dentist's office or in a lab, you can actually choose the wavelength of the X-rays very precisely. And this allows you to choose the wavelength so that certain special atoms in the structure have dramatically different properties. And by using that phenomenon, you're able to solve the structure. It's somewhat complex. I've tried to explain it in the book, but really it's actually beyond a popular book. It's a technique called anomalous scattering. But the main point that I hope you would get if you got the book is that I realized that it had strong enough signal that you could probably use it to tackle a very large molecule like the ribosome. And so I had this idea, and ever since that idea hit me in the head, I couldn't then get it out of my head. And then at some point I realized I have to go for it, because I thought it was a secret idea of mine, it would give me an edge, and so on. Actually, in science, very few ideas are really secret. I talk at the end of the book about how what happens is, in science, the state of knowledge and technology reaches a certain stage. And at that point, a few people realize what's possible next. And so it's not an accident that, for example, calculus was discovered simultaneously by Leibniz and Newton, or the theory of evolution by Darwin and Wallace, or quantum mechanics by Schrödinger and Heisenberg and several others. You know, this is because the state of science has reached a stage where that progress happens. So not surprisingly, what I thought was my secret silver bullet also occurred to, you know, J.B. Cate, who was working with Harry Noller, and then he told it to my, you know, my former mentor, Peter Moore and Tom Stites at Yale. So the three of us were all working away with our secret idea, but you know, it was the same idea, okay? And but anyway, given that idea, I felt that I had to try and get it to work, and that led to my working on the project. And then we had 2 days of beam time at a synchrotron near Chicago, so we had to fly out there from England with our crystals. And when you're given 2 days of beam time, you don't just take breaks, you know, you don't go to sleep. What you do is you work in shifts around the clock so that you're using the full 48 hours. And at the end of the 48 hours, I did a calculation, and it turned out there was no signal. And I thought, oh my God, we're going to be completely scooped, and you know, this is going to be terrible. And then I noticed that we had made a little typo in the script. And as soon as I corrected that, you know, the computer went off and churned out all these peaks, showing that these special atoms we were looking at were all there, and the signal was terrific. And that's when I knew, even without doing the calculation, that we'd solved the structure. And we had no sleep for 48 hours, and so somehow all the tension of the previous year, and actually certainly the previous several weeks, was suddenly released. And I just sort of jumped up and started dancing around the office saying, you know, we're going to be famous. And then I had this technician who just didn't know a whole lot. He didn't quite understand how important this thing was. And he just sort of looked at me as if I was completely insane. I still remember the look on his face.
Well, at least you didn't emerge naked from your bathtub and run on the streets. Thank God for that. But, you know, from this lovely little story, this inspiring little moment of joy, I want to move on to something slightly darker. You write rather admirably in your book about the sort of intense pressure, the competition, the insecurities that scientists have to face in the race for recognition. Could you talk a little bit about that? What's the worst you've seen of it? And personally, how did it impact you personally and professionally, particularly when you were pursuing this? I mean, like you said, no idea is entirely novel, and there were other people working on this as well. And were you ever anxious that your work might not be able to keep pace with some of your colleagues, in fact, who you ended up sharing the Nobel with eventually?
Oh yeah, it's very stressful. But I'll start off by a little comment my wife made. You know, occasionally I would tell her I was really worried about being scooped. So at one point she said, "What do you mean by scooped? You're not a journalist." And I said, well, you know, there are these other groups working on this problem, and you know, if they publish first, then you know, we can't publish our results. So she looked at me and she said, "Well, if there are other people working on this, why don't you do something original?" And so, you know, my wife has a rather common sense attitude to life. But the reality is that, you know, if we could think of a problem that nobody else was working on and was interesting, that's great. But that's very, very rare, because if the problem appears to be interesting to you, then it's likely that other people will be interested in it, because it is interesting and important. And science is, you know, an open you know, marketplace. So what happens is, you know, we think of scientists, but not we, but the public thinks of scientists in several ways which are mistaken. They either think of them as Spocks. You know, I don't know if you know Star Trek, but Spock was an alien, and so he was completely rational. He didn't have human emotions. So we're not Spocks, we're human beings. At the same time, we're also not saints, you know, so we are motivated by a complex mixture of you know, goals. We're motivated by curiosity. Sometimes we're motivated by wanting to do good by discovering, say, a cure for cancer or something. Other times we are motivated by wanting to make a lot of money. You know, say you make a discovery and then, you know, you start up a company and it, you know, goes well and you make a lot of money. And but we're also motivated by ambition, by the desire to be first, by the desire for recognition. I think all humans want to be recognized. You know, they want to be thought of as good at what they do. And the way scientists are thought of as good at what they do is that they, you know, make discoveries and that people appreciate. So this leads to real tension if people are working on the same field, because in science, you know, if there are several types of science. Some kinds of science are very, you know, original. There's nobody else really who's doing exactly what you're doing. But if you're looking for the structure of a molecule, the molecule has a structure. It's not going to be different whether you found it or somebody else found it. The result is going to be the same. So it's has more in common with what I would say, you know, being the first to climb Everest, or being the first to, you know, discover the source of the Nile. So it has more in common with that sort of discovery, you know, exploration. And so there, you know, the competition is almost a winner-take-all situation. The first person to discover it and publish it, you know, if you come second, the most you could say is, oh, that person was mostly right, but actually he got parts of it wrong. But that's not really a big deal. It's not very satisfying. So there's a strong pressure to come first.
Okay, so, you know, the thing is that one of the things that you spoke about recognition and scientists wanting to be recognized, and of course, the final frontier in this recognition is seen to be the Nobel. It's supposed to be this life-changing moment. And you had the experience of winning the Nobel, which is fantastic, but you also chose to draw attention to some of the flaws of the prize as it exists today. Why did you choose to do that? Could you talk a little bit about this?
Oh, I think I really dislike the whole idea. I think, you know, it makes scientists, especially top scientists who've done great things, when they should be sort of very happy and celebrating, they become anxious because of this, you know, prize. And I talk about why that is. It's because the Nobel Prize has achieved a sort of cachet that no other prize has. There are now prizes which pay much more than the Nobel. For example, the Breakthrough Prize is, I point out in the book, is about 8 times the cash value of a shared Nobel Prize. But really the public, if you tell them the Breakthrough Prize, they have no clue what it is. And it's because of the history of the Nobel Prize. You know, when it was instituted, it coincided with great revolutions in physics, chemistry, and biology. Physics had just discovered quantum mechanics and relativity and all sorts of things, you know, atomic structure of matter, fundamental particles. So, and then chemistry had discovered, you know, the molecular basis of bonding and valence and all sorts of things that were fundamental to chemistry. And biology had discovered genes and genetics and had then tied in with chemistry. So we had these big revolutions. So many of the early Nobel laureates were really amazingly great scientists. So people started confusing getting a Nobel Prize for being great. Okay, that's no longer necessarily true. It's actually very seldom true. But because of the history of the prize, that's what happens. And so everybody wants to be then associated with that. And so there's this real hankering among a lot of scientists, whether they admit it or not. Some of them pretend to be very blasé and, oh, I don't care about that. But actually, I deep down, they probably do care. And some are much more open in their hankering. And I call this disease called pre-Nobelitis, which is, after you've done some really important work, you're sort of anxious about whether you get the Nobel Prize or not.
And it's incredible that you could speak about this so honestly and courageously, of course. But when one reads your book, one gets the sense that a lot of triumph of science is deeply linked with the triumph of tools and methods as well. You yourself went from neutron scattering to X-ray crystallography, I can never pronounce it correctly, to high-resolution electron microscopy. Could you talk, and this may not be a fair question to ask you to answer briefly, but could you talk a little bit about this sort of synergy between science and tech?
I think the two go hand in hand. They're completely intertwined. So people used to think that fundamental science leads to applied science, which leads to technology. That is not true, because technology itself drives new discoveries. I'll give you a classic example. So superconductivity, very fundamental, discovery in physics. This is the idea that at very, very low temperature, there's no resistance to current, so you can have extremely high currents. That itself led to very, very powerful magnets, because you could have very, very high currents by making the magnetic coils cold so that they were superconducting. So when you have strong magnetic fields, you can use that to do a technique called magnetic resonance imaging. Everybody knows that you can go to a doctor and they can do an MRI on you, okay? And so that's one example. And then MRI is a discovery which makes all sorts of medical discoveries possible. But then these superconducting magnets are used to power particle accelerators. They need very, very high magnetic fields for these particle accelerators. And with those, you can make new discoveries. You can have synchrotrons that make new discoveries like the ribosome, or you can have the discovery of the Higgs boson. So I've shown you how fundamental discovery results in technology, which results in new fundamental discoveries. So they're intertwined all the time, and science really advances by technology. But technology also requires science. New technology also requires new science. So there's a complicated web by which they advance together.
We've been talking perhaps a little bit abstractly, though I know you've tried to be as clear and simple as possible when talking about your research and your science, but perhaps you could talk a little bit more about the real life implications and possibilities of the discovery that you have made and your colleagues have made for real life problems, particularly in countries like India.
Yeah, so first of all, I should say, most of us who study the ribosome get our funding from, in the West, in the US, from the National Institutes of Health, or in the UK from the Medical Research Council. So we would dutifully write at the beginning of our grant that the ribosome is the target for lots of antibiotics, and if we work on the ribosome, maybe we will understand how these antibiotics work and maybe help design new antibiotics. But I have to say, none of us believed it. This is just something we wrote because that's why we get grant money. Okay? But it turns out that completely without realizing it, we were telling the truth. Okay? And because the structures of these ribosomes have now been used by us and by many other people to solve the structure with antibiotics bound to it. And knowing how these antibiotics actually are bound allows people to decide how to make molecules that might bind in the same pocket, but even better, or even when you have resistance. And my brother-in-law, who's also a scientist, showed me a recent paper, actually 2 papers, where they've used the structures we've done to design new antibiotics that are effective against tuberculosis in culture. Now, from that to a medicine is a long road, because you have to be able to synthesize it cheaply, you have to have the right properties that it can be absorbed. Above all, it can't be toxic, it has to be deliverable to the bacterium while you're infected. These are all big problems. But the point is, it does offer, a route to discovering new antibiotics. And that's true of a lot of biology, not just the ribosome. Looking further ahead, the ribosome makes a particular kind of polymer, which are proteins. But knowing what the ribosome looks like, it might be possible to engineer it so that it makes completely new types of polymers. So you might be able to make polymers in a very, sort of what I would call an environmentally friendly way, without the use of nasty chemicals and so on. So that's sort of looking further ahead. But I should say, you can't predict where your discoveries go. I'll give you a classic example. Einstein, when he discovered the general and special theories of relativity, this is about the fundamental fabric of space and time. It's how time, the concept of time changes depending on whether an object is moving away from you or towards you. Now, or how space warps near objects. Now, nobody had imagined this would have any practical applications. And yet, every time you look to see where you are by using a smartphone, you have to realize you would not be able to do it without the theory of relativity. And the reason is that this GPS signal, which allows you to tell you where it is, involves looking at the time signal from multiple satellites. But it only works if you correct this signal for the movement of the satellites relative to the Earth using relativity. So if you didn't correct it, the GPS signal would drift off, and within a day, your dot, which actually tells you in the Leela Palace, would maybe be in Mysore or something.
That's absolutely fascinating. And you're right, whenever one thinks of ribosomes and the research that has gone into the structure of ribosomes, the first thing that comes to mind is prevention of disease, diagnosis of disease, and cures of disease. But for countries such as ours, could there be other directions in which we could consider the application of this knowledge, perhaps in making agriculture more sustainable, which is a pressing economic issue, beyond economic issue in this country, really?
I think that's the application of ribosome research for antibiotics. I would not say that's an Indian problem. But I think India has a serious problem with antimicrobial resistance. In fact, the whole world does, but I think in India the problem is fairly acute. And there are many aspects to this. Some of it is social, for example, sanitation and hygiene to cut down on infections. Another is the misuse of antibiotics. I came down with a chest infection, and I went to a doctor and was prescribed antibiotics. But I found that actually I could go to any medical shop in Bangalore and get almost any antibiotic I want, okay? And many people will take it when they have a viral infection and when antibiotics aren't actually useful, let alone needed. And so, I think so we can prevent the abuse of antibiotics, we can prevent the use of antibiotics in animal husbandry. Certainly in the West, I don't know if this is true in India, but cattle that are raised are fed antibiotics to fatten them up. And that's a real abuse of antibiotics. So there are many things we can do to try and sort of curb the use of antibiotics and to have good health practices that minimize the spread of infectious disease.
It's absolutely true of India. The use of antibiotics and animal husbandry is a huge problem, in fact. But speaking of India, I am going to veer a little bit away from science that we've been talking. This is concerning science, but I'm going to talk a little bit about the history of science. Back in the colonial era, we had scientists such as Bose, of course, Meghnad Saha, C.V. Raman, and these were all incredibly illustrious scientists. And this is not to say, of course, that India does not have illustrious scientists at the moment, but do you regard any particular era in India to be the golden age of science?
Any particular,
era in India to be the golden age of science? Did we ever have a golden era of science?
Well, I think it goes in waves. I think there was a burst. And I'm not a historian, but my theory is that that early generation of Indians who were by and large either trained by the British or, absorbed British knowledge brought by colonization, they were eager to show that they were just as good as anybody else. Because up to that point, there was this feeling, because of colonization, the British thought of Indians as all these, backward natives, they're not as advanced as we are, etc. And I think, people like Bose or C.V. Raman or Saha or S.N. Bose, these people were saying, actually, we're just as smart as anybody else. And I think there was this really strong motivation on their part to sort of prove themselves. That might have been a driving factor in their success. I think after independence, India went through several phases. I think they made some bad decisions, for example, in the way science was funded, in the way that research had drifted away from universities, so that young students were not exposed to the highest level of research, because that was done in institutes rather than in universities. So there were lots of what I would call policy decisions. But I think now, that many of those decisions are being corrected. For example, the Indian Institute of Science here has launched an undergraduate program a few years ago. And India has decided to set up these ICERs, which combine undergraduate education with, high-level research. So the hope is that, a new generation will take off and be very ambitious. I think part of the problem is when conditions were hard and there's not enough funding, when there's, there still is too much bureaucracy, it sort of saps your energy and it saps your ambition because you're constantly fighting just to get whatever little work you can done. And if it saps your ambition, then it automatically changes your sort of goals. And I think that's the thing that India needs to really recover in a big way, which is to really become very ambitious. And I see that happening in China in a big way. China, the best universities in China are really very ambitious. They want to be the best in the world. They don't want to be the Harvard of Beijing. They want to be themselves. They want Harvard to be the new Tsinghua of Massachusetts. So I think that's their goal, and they're putting a huge amount of resources into it. They're attracting top Chinese scientists back with big packages and resources, and so I think India has some advantages. It has a very young population, which is what you need if you want to go into new areas and develop it. And it is a democracy which I believe is good for science, because science depends on freedom of thought and being able to say what you think and questioning authority and so on. I think that's a good atmosphere for creative science or creative anything. So India has some advantages, but if it's not careful and gets kind of bogged down in bureaucracy, or even worse in kind of what I could think of as these sectarian squabbles, which are a sideshow, then it'll inhibit progress. It needs to keep its eye on the future and say, how can we come together as a nation and really progress? That should be the goal.
There are many different things that could be holding back. Thank you. The development of, we have just about 5 or 6 minutes left, so I'm just going to be a little bit quicker with my questions. There could be many different things that could be holding back the development of science in India. I mean, there's socio-cultural mores, there's of course, economic pressures. I mean, we're still relatively a poor country, and one can't disregard that. There are problems with education in primary education, secondary education, higher education. But when it comes to ambition, if I'm not mistaken, I think Prime Minister Modi made a very ambitious statement that by 2030, India is going to be one of the top 3 countries when it comes to science and technology. Some problems might be harder to solve than others, for example, the state of the economy or sociocultural mores. But can you think of a couple of very specific policy measures, or perhaps even private sector measures, private funding perhaps, that can be taken that might be able to help this goal actually become a reality?
Yeah. So you mentioned that there's funding because India is still a relatively poor country, but the reality is, even if you take it as a fraction of GDP, India lags well behind advanced science countries. It lags well behind China, lags quite a bit behind South Korea, lags behind Britain, and Britain is not that high up in terms of fraction of GDP per science, although they're planning to try and increase it dramatically. And so, so I'll give you an example. In Britain, they want to go from 1.7 to 2.4% of GDP on R&D. In India, I believe the number is about 0.7%. Now, it's even worse because in most of those countries, government spending is only about 1/3, and about 2/3, or possibly even more, 2 to 3, private spending is about 2 to 3 times public spending. Here, it's exactly the opposite. Most of the spending is government spending. The public spending is really quite small. And so, really, the companies in India, all of the big corporations in India, they should be promoting R&D in a big way. How else are they going to be competitive? Otherwise, they'll just be sort of plateauing and eventually lose their edge. And India also needs to promote an entrepreneurial culture. We have to allow people to try to start companies and fail time and time again, so that they gain experience and then eventually succeed. So these sorts of things, I think, are what's going to be needed if India is going to be in the top 3. The reason it might have a chance to be in the top 3 is simply scale. India has a scale unlike most countries. It has 1 billion people, a huge market, internal market. So these are all reasons why it could succeed, but it won't succeed unless these other ingredients are there.
And would you also think that we need to try and create our own IPs? I mean, is that something that you feel is
create our own
intellectual property? Is that something that you feel is important?
I think all countries, because it's a global marketplace, and so if you have something that you're making and you don't want to be somebody to simply rip you off, you have to protect it by IP. And also, IP is important for another reason, and that is many venture capitalists won't fund you unless you protect your intellectual property, because if it succeeds, they want not to be able to they want to be able to sue anybody who tries to copy it.
Absolutely. You mentioned freedom of thought and the dangers of sectarianism. As ambitious as the Prime Minister's statement might have been about India becoming top 3 by 2030, he's also the head of a dispensation that seems inclined towards what can be best described as pseudoscience. You yourself, it's reflected in the way the character of a lot of institutions is changing, and you yourself expressed some dismay regarding the way the Indian Science Congress was being conducted. Is this do you view this simply as something that's part of just one political cycle, or is this something that you feel as a nation we should be a little bit more deeply concerned about?
I think, first of all, there's pseudoscience everywhere. There was a British guy who published a completely flawed paper suggesting that vaccines are dangerous, and now he's promoted a whole anti-vaccine movement which is resulting in the deaths of thousands of children. And so there's pseudoscience everywhere. It's not restricted to India. But there are a couple of things that make one concerned. And one is, if you have a large scientific meeting which has a tradition that on the first day it's addressed by the Prime Minister, then that meeting should not be used as a platform for pseudoscience. Because that gives it a kind of credibility that it otherwise wouldn't have. And so that's something that really needs to be rebutted very quickly. And one thing I always say is that there are 3 Indian science academies, and they really need to, when this sort of thing happens, they need to rebut it in the media almost immediately. They can't wait around and let it become a big story. The other is that if people in positions of authority, for example in government or vice chancellors of universities, I'm told, if they indulge in this sort of stuff, they're people in positions of authority, and they may be taken seriously by people who don't know any better. And that is also a serious issue, and that also needs to be called out. So I think most scientists in India, vast majority, it's not affecting their lives, etc. But it's a question of what is the perception in the public? How does the public think about this? And also, what sort of image do we want to project to the rest of the world? What does India want to project to the rest of the world? Those are, I think, serious matters. And so these sorts of things need to be, rebutted head on.
Of course there's pseudoscience everywhere. I remember a time when Prince Charles wanted the already strained NHS to include homeopathy. But to your point about rebuttals, I really wish I wanted to talk to you about the role of the scientist as a public intellectual, but I don't think we have at the time. But I cannot possibly let you go without asking you, as President of Royal Society, how you think Brexit might impact the future of sciences in Europe and UK. I know that this may be a difficult question to answer. We don't know when Brexit is happening or what is happening with it.
Most scientists, about 90% or so of scientists in Britain voted to remain. And even if many of us had some issues with the EU, bureaucracy or various regulations or something, we felt that on the whole it was a good thing because it promoted freedom of movement, freedom of ideas, exchange of ideas, collaborations. It also promoted large-scale projects that individual countries would have trouble by themselves. So on the whole, it was very good for science. It was also very good for Britain. Britain became a magnet for some of the best scientists in Europe. Britain always is at the top of, if you look at success rates in EU grants, Britain is always at the top. And many of the people they fund, though, are from other parts of Europe who come and work in Britain. So it's been very good for British science. Now, our efforts, and the British government has accepted that, is that if we leave the EU, and of course, I have no idea what's going to happen now because everything is in flux, but if we leave the EU as was planned, then what we want is the closest possible ties with the European science community. So we want to be on a pay-as-you-go basis, continue to be part of EU programs, and continue to welcome EU scientists, and of course scientists from all over the world into Britain. You know, traditionally Britain has been a fairly open society. It's second only to the US as a destination, international destination for science and research. And considering it's much smaller than the US, that says quite something. And you know, it is not many countries that would take a person who has immigrated very late in life, in his late 40s, and elect them president of their distinguished academy. You know, that shows you the kind of openness and meritocracy that exists in Britain. And what we in the science community and the Royal Society would like to do is preserve that feature of Britain.
Well, here's hoping that we'll succeed in doing that, and not just that, the sort of anti-immigration, sentiment that is, rippling through UK, Europe, US, and now perhaps India as well will subside in time. And are you hopeful about that as well, would you say?
I'm cautiously optimistic.
Cautiously optimistic. How German of you.
Spoken like a politician.
Yes, absolutely. Thank you very much.